So here we starting from descriptions of a stress element. Let me draw this element bigger. So if we consider this as a small stress element, and this element represents the local distributions of the stress, and so for example here we give ourselves the local coordinate system xy like this. And so in the x direction, we, from the previous few chapters, we might be able to analyze the distribution of the stress in x direction. Let me say that is sigma x. In y direction, let me say that is sigma y. And then in the shear stress, that is the tau xy here. And this one is under static equilibrium. So basically the sigma x, this amount should be equal to this one. Sigma y, this amount equal to this one. And in shear stress, the fork amount must be in equilibrium. So that is a given situation. And the transformation of the stress study is this. And here I have a little the 8 of this. So imagine this is the coordinate systems, and say this is a stress element right now, and I just use papers. So for example, if we want to rotate, we want to study the distribution of the stress in such a rotation. So it's overlapped a little bit. I'm not seeing clearly. Let me move out to here. So again, original configuration of the stress element is in xy directions. Now if we rotate, say by any angle theta, so this element we imagine to rotate respect to the center, the origin of the coordinate systems, rotate by that. We want to know what is the new distribution of the new stress in new x directions, in new y directions. Okay, so so that is our goal. And again, this one, we want to rotate by a certain angle. We want to find the distribution of the stress. And most of the time, to avoid the confusions of the overlap drawing in schematic representations in this textbook, and actually in all the textbook, we extend here is a good practice is we try to extend this transformed element out a little bit, giving ourselves more space to represent the calculated distribution, the information. So usually what we're doing is here. So here we, for example, we are given the, say, the new and the rotation of the angles. So to this orientation, this is the rotate element, and here this is from here the x translate to here, so this is our new x prime direction. Y rotate by angle to here, so that is our y prime directions. Okay, so that is called the transformed stress element. In this element, we are interested in knowing what is the new the normal strength in x prime directions and what is the y prime. And so again, here in balance, and also we want to calculate is the corresponding x prime, y prime. And this one, you can imagine this is a function of the angles you rotate. Okay, so here for the stress, for these topics, we studied these problems. We are given the normal stress element sigma y and tau xy, and also we designate any angle of rotations. And for theta rotation, we define positive if we rotate counterclockwise, otherwise negative. So for this one, we're going to calculate is what is corresponding the transformed stress in the new orientation, which is a function of the theta. And in these chapters, we're going to learn two techniques. One is through calculations of the stress equilibrium, the force equilibrium, to formulate the three equations in terms of the given information. The second technique we're going to learn is to use what we call the Mohr circles. And Mohr circles basically is we build up based upon the given information, the centers is at the sigma x plus sigma y divided by 2, 0. And the radius of the Mohr circle is based upon the given information, that is sigma x minus sigma y square tau square. So with the two informations, we can build up the Mohr circle. Let me put a little bit the circle here. So that is a circle, and in the coordinate system, sigma x and tau x y coordinate systems. Okay, so here is our location of the centers based upon this coordinate. And the first coordinate representing is the normal stress. The second coordinate representing is the shear stress. And with this magnitude or here, you can draw a circle in this spatial coordinate systems. And from there, all the information about the transformation of the stress can be covered by any point on the circles. And that is the key point. You need to learn how to represent a point on the Mohr circle to the distribution of the stress in element here. Vice versa, if you have a distribution of the stress on the stress element, how can you represent that information onto the Mohr circle? And then using the information of the theta on the Mohr circle to help you to calculate the three terms. And that is the topic you're going to pay attention in these chapters. Thank you.